All right. So 4.1 part 2, we're going to talk a little more about arc length and angular speed. All right, so let's recap just very quickly what we talked about on Friday a little bit. We talked about this idea of a radian. And we said for a radian, we are saying our angle in radians is the arc length over the radius of our circle. And one benefit of using radians is the radians rely on the properties of circles rather than subdividing a circle based on how many days there are in a year and that kind of thing. So that we've used that for lots and lots of years, but using radians gives us a little more natural way of dealing with angles because it has to do with the properties of circles. And we defined one radian as the arc length, or the angle where the arc length equals the radius of the circle. So that we got one radian when our arc length equaled the radius of the circle. And that led us to the idea that there are 2 pi radians in a circle. That's where the 2 pi and the angles there. That's where they're connected. All right. So, and we rearranged this formula on Friday also, but we're going to talk about today. We're going to use it to talk about arc length rather than the angle. We're going to say that the arc length is the radius times our angle when theta is in radians only. So this property relies on our angle being in radians. Our angles have to be in radians. This doesn't work if our angles are in degrees. And we said one of the other nice things about our using radians for our angle is because arc length and radius have the same units, length, inches, meters, millimeters, centimeters, whatever, that an angle in radians does not have any units. Because I have inches over inches, the units go away. So radians don't have any units, so we don't have to worry about units. So we're able to use this formula to decide to figure out arc length if we're talking about a certain angle in a circle. So let's look at an example. And I want to write out this example how in the way that you might be asked this question, so that when you see the terminology, you understand what it's asking. So we want to find the length of the arc that subtends a central angle of 120 degrees in a circle with radius 5 inches. So this is an example of the type of the way that a question about arc length might be asked. Find the length of the arc that subtends a central angle. So it helps draw a picture. So if I draw a picture of this situation, there's my circle. No, it's not a perfect circle. And here's my 120 degree angle. It says this radius is 5 inches. So what this question is asking us is, what is this arc length? That's what it wants us to find. So there are a couple of different ways that we could approach this problem. The first one is we can use this formula. The arc length equals the radius times our angle in radians. So let's use that one first. Our arc length equals 5 times, we need our angle in radians. So I'm going to go over here and we'll do that 120 degrees. How do we convert that to radians? Times pi over 180. And if I reduce this fraction, 2 pi over 3. So I get 2 pi over 3 radians. 2/3 pi, it's the same thing. So if we were doing this question without a calculator, this would be our angle in radians. So our angle equals 5 times 2 pi over 3, or our arc length is 5 times 2 pi over 3. And when I multiply that out, I get 10 pi over 3, and my units would be what? Inches. So this arc length, the length of this arc would be 10 pi over 3 inches. If the question asks us for an approximate answer and we could plug it into our calculator, we would get that that's approximately 10.47 inches if I multiply that out. What's another way that I could approach this problem? What do you think, man? So you're talking about make a triangle, okay? So you're taking your circle and you're drawing a diameter.
No.
No? Right. Connect here. Okay. I'm just trying to see how you're thinking. What do you think?
You could find the whole circumference divided by
Okay. So Monica says, let's find the entire circumference of the circle. And then we find the fraction of that circumference that 120 degrees takes up. So what's the circumference of the entire circle? 10 pi. And 120 degrees is what fraction of a full circle? A third. So we get 10 pi over 3. Same thing. So this was the route that I would think was the other route that I saw, is figure out the fraction of the entire circle, and that's essentially what we're doing here. This conversion tells us what fraction of the circle 120 degrees is. All right, any questions on that example? Okay, let's talk about angular speed. All right, so our arc length, we said, is r times theta when theta is in radians. Thinking back, very basic, what's our most basic idea about speed? Speed is, how do we find speed? Distance over time. Speed is how far we go divided by how long it takes us to go there. So speed Distance divided by time. Well, our arc length is a distance. So we could talk about the speed in terms of the arc length. So if I divide both sides of this equation by time, our radius isn't changing. This tells me that this arc length is a distance. We call this part the linear speed. And this, in the book they call it linear velocity. I'm saying speed because slightly more accurate to say speed. Velocity has to do with the direction also. So this is our linear speed. We call theta divided by time the angular speed or angular velocity. And the way that we usually write this equation when we divide both sides by time is we use v for velocity equals r omega, where omega equals our angular speed. Yes? And our units of angular speed are radians per unit time. So our linear speed is distance per time. Our angular speed is radians per time. So radians per second, radians per minute, radians per hour, something like that. So this gives us a way to relate the linear speed of an object to the angular speed of something that's turning on the object. For example, a bicycle. The linear speed has to do with the arc length, how far the tires are traveling as we ride along, and the angular speed tells us how fast the wheels are turning. And the angular speed depends on the radius of the wheels. A smaller wheel is going to have to turn faster to cover the same distance as a larger wheel. So the smaller wheel is spinning more radians per second to cover that distance. And the way this is omega is this letter. It's a Greek letter. So we usually say V equals R omega for angular speed and linear speed. And the problems that you'll see with this usually have to do with something like a bicycle, something like a car, maybe a saw blade in a sawmill that's turning, that kind of thing. So something that's turning and moving at the same time. So let's look at an example of using linear speed and angular speed. So we have a car, and it's traveling at 65 miles per hour. With 15-inch tires. We want to know the RPMs, revolutions per minute, of the tires. So our car is traveling at 65 miles an hour, got 15-inch tires. We want to know what are the revolutions per minute of the tires. So we have a couple of steps that we have to go through here. Anybody see what are some of the things that we're going to have to deal with in this problem? We have our linear speed is in miles per hour. Miles per hour. The answer, we want the answer in revolutions per minute. So we need to deal with the hours and the minutes part. What else? There's another thing that's kind of similar. Our speed is in miles. And our tires, I guess I shouldn't say answer, our tires are in inches. So we need to get everything in terms of 1 unit. So we need to convert, what I want to do is convert 65 miles per hour to something in inches per minute. So the inches match the units of my tires, and the time matches the units of my answer. So we need to do this conversion. I'm going to write it as miles per hour. How are we going to convert? Let's do the miles to inches first. How can we convert from miles to inches? Convert it to feet. So how many feet are in a mile? 5280. Hopefully we remember that because we talked about Denver being a mile-high city. We're 5280 elevation. So 5280 feet per mile. And how do we convert feet to inches? Multiply by 12. So we multiply 5280 times 12 to get the number of inches in a mile. So if we multiply that out, so 5280 times 12 turns out to be 63360, and that gives us inches per mile. I'll put an I there for mile. And then we need to deal with the hours and the minutes. So what are we going to do for that? We need a per minute, so we need minutes in our denominator. 1 hour per 60 minutes. So this is going to be our conversion from 65 miles an hour to inches per minute. So when we convert this, we finally get, when I multiply that all out, 68,640 inches per minute. That's how fast we're traveling in inches per minute when we're traveling 65 miles an hour. So that's our linear speed. And we need our angular speed. So let's find our angular speed. So that's our next step, is find angular speed. So from our equation, we know that 68,640, our linear speed, equals the radius of our tire, 15 times omega times our angular speed. Divide both sides by 15 and I get omega equals 4576 radians per minute. Are we done? What did the problem ask us to find? It asked us to find revolutions per minute. So we know we're turning 4576 radians per minute. How many radians per revolution? 2 pi. 2 pi radians every revolution. So I'm going to do 1 revolution per 2 pi radians. So I'm dividing by 2 pi, and I finally get omega equals, I'll write it underneath, 7228, sorry, 0.29 revolutions per minute. So when we're traveling 65 miles an hour, a 15-inch tire is turning around 728.29 revolutions per minute. We converted our linear speed to an angular speed of the tire. Questions on that example? All right, so before I give you your homework, I just want to talk about one other kind of problem that often trips students up. So this problem asks us about 2 cities on the surface of the Earth. And the question often will tell us that one city is, and here's our North Pole, one city is directly north of the other city. And it asks us something about the difference in their latitude. So we're on the surface of the Earth, and it might ask us about the difference in their latitude. Or it might say something about their difference in their latitude and ask how far they are apart. How would we go about solving this problem? What do you think, Stephen?
So if you take a slice of that circle along the two-dimensional line,
Okay.
and make that the circle and then find the...
Okay, so what we're going to do is I'm going to cut through the globe here, and I'm going to draw that circle sideways. So I'm making a cut through here where the circles are, or where the cities are, turning that sideways. On this picture, the cities would look like this. Here's the center of the Earth. That angle is the difference in their latitudes. And this distance between them is what on that circle? What thing that we've been talking about? The arc length. That's the arc length. So a problem that's asking you about 2 cities that are directly north, one is directly north from the other, is an arc length problem. So a lot of times it takes a little bit for students to see that the first time they see this kind of problem. So 2 cities directly north from each other, that's an arc length problem. All right, homework. There you go.